All right, so today we're going to talk about a new thing called an eigenpair. And before I start that conversation, I just want to explore something a little bit. So here I have my little 2 by 2 matrix grapher. I'll throw a link to this in the video description. This is just a tool that I use for graphing the inputs and outputs of a 2 by 2 matrix. So here I've got an input vector that I can drag around, and I can see that output vector gets dragged around. This right now is the matrix 3, 2, 1, 4. So that's 3, 2 is the first row, 1, 4 is the second row. And I'm just kind of playing with this. And I noticed that there's a couple of spots where the input vector crosses the output vector. So like this one here. And what this means is that essentially the matrix just like takes this input vector and just like makes it longer. I noticed there's another one of those over here as well, right? That's where this blue vector just gets made longer. So, like, what is the deal with that? It feels a little funny. That's kind of what we're here to talk about. So let's write down what it means to just have a matrix that makes a vector like longer, right? So I'm looking at taking a matrix, I'm doing it to a vector, and if I'm seeing that behavior, there's some scalar lambda that's getting multiplied by x. So this is where the matrix x actually just acts like scalar multiplication. This is really kind of interesting to me. This is a cool thing. So the trick here is like, can I find a pair of these? So I've got a little plan for that basically. So first I'm going to do a little vocabulary. So the vocabulary is that an x like this is called an eigenvector. And the lambda here is called an eigenvalue. And then personally, I have a habit of calling lambda and x together, right? This quantity here. I call this an eigenpair. This isn't like extremely standard notation, but it's pretty popular notation, or a pretty popular word. I'm not like a person who invented it or anything. You just, depending on who you take linear algebra from, they may or may not say the word eigenpair. I'm going to say the word eigenpair a lot because I find it to be a really useful concept. So I've got my eigenvalue, that's my scalar, right? That's how much the vector gets longer or maybe shorter by, or maybe like, I don't know, there's some other weird stuff that could maybe happen. And then the eigenvector is just telling me what the input is. Now, I should probably notice that if I put in a multiple of x, right, if I scale x, I still get this relationship, right? So thinking here, if I just drag this red vector in or out, right, that's me just scaling the input vector, that behavior stays the same. That's kind of to be expected because a matrix is a linear operator after all. So let's talk about finding an eigenpair. So the way I'm going to go ahead and locate an eigenpair is I'm going to look at this equation. I'm going to manipulate that a little bit. So I'm going to say ax minus lambda x is equal to the 0 vector, right? So I performed a little bit of vector addition to both sides, right? I added the vector negative lambda x to both sides here. Really like to factor out an x from this equation. So I'm going to kind of set myself up to do that. And I'm wondering, what is it that I'm going to get when I factor that x out? So out of this first term, I'm pretty clear that I'm going to get an a. And it seems relatively obvious that you should put a minus lambda here. That's going to be wrong. It's a good idea. It just doesn't happen to work, which is kind of a problem. So the reason it doesn't work is that a, in order for me to think about this at all, a had to be a square matrix. Lambda is a scalar. You can't take a matrix and subtract a scalar from it. It doesn't work. So what I need here is for this to match categorically, right? So what I'm going to do is I'm going to actually make myself a little bit of space here. And I'm going to rewrite this equation one more time. I'm going to rewrite this as ax minus lambda ix equals 0. And then when I factor that x out, I'm going to get a minus lambda I. And now, because these are both matrices, I can actually do this calculation. So looking at this, what this means is that X is in the null space of A minus lambda I. So this is my key for finding eigenpairs, right? So the thing I'm going to do is I'm going to set A minus lambda I. Well, I really want to set A minus lambda I x equal to 0, but that gives me too many things to solve. So what I'm going to do first is I'm going to say, all right, if there's something in the null space, that means the matrix is singular. So I'm going to set the determinant of A minus lambda I equal to 0. I'm going to solve that. That's going to give me lambdas. It's going to actually give me maybe more than one lambda. And then after I've found the lambdas, I'm going to take A minus lambda I and augment it by 0. And then I'm going to reduce this. This is going to let me find my x's. There's going to be an x for the lambdas. This is actually a little bit of a lie, but generally they come in a lambda gives you an x. It's not totally true, so take it with a grain of salt for now. We'll talk about the nuances later. For right now, just know that this is my general procedure. So I'm going to take that matrix that I had a minute ago. That matrix I had a minute ago was 3, 2, 1, 4. Right, so this is going to be my example. And my goal is going to be to find the eigenpairs. Okay, so my first step is I'm going to take A minus lambda I. So A minus lambda I is going to be 3, 2, 1, 4 minus lambda 0, 0 lambda, which is going to give me 3 minus lambda, 2, 1, 4 minus lambda here. And the thing is, at no point later are you ever going to have to write this chunk out. Just subtract those lambdas down the diagonal. It's real chill. Then I need to take the determinant of that matrix. So the determinant of A minus lambda I is going to be 3 minus lambda times 4 minus lambda minus 2 times 1. Okay, now I'm looking to set this equal to 0, so I'm just going to FOIL this out a little bit. So I'm going to get 12 minus 4 lambda minus 3 lambda plus lambda squared minus 2. Then I'm going to go ahead and fiddle this around a little bit more. So I got lambda squared minus 7 lambda plus 10. And then I'm looking to set this equal to 0, so I'm going to factor that. That's going to be lambda minus 5 times lambda minus 2. That's going to tell me that my lambdas are 5 or 2. Okay, now I'm going to go ahead and find those eigenpairs. So I'm going to take this matrix, this matrix here, and I'm going to say, all right, now I'm going to work with the lambda equals 5 case. So I'm going to paste my matrix down here, and then I'm going to drop those lambdas. So I'm going to say, all right, we are no longer talking lambda and lambda here. We're talking 5 and 5, right? So I'm subtracting this lambda of 5 from both bits. It's going to be the same lambda throughout the matrix. Don't use them both at the same time. We're going to do lambda equals 2 over here in a second. So this is going to give me a matrix. That matrix is going to look like negative 2, 2, 1, negative 1. This matrix had better be singular. If this matrix isn't singular, you probably accidentally factored wrong or solved wrong or something. So someplace along the line we lost a lambda if this isn't singular. Luckily this one's singular. I can grab either row here. They're both the same. So I'm just going to say, all right, let's take this thing. We'll do negative 2, 2, 1, negative 1, augmented by 0. I know one of these rows is redundant. So I'm just going to grab the equation out of the second row. That second row equation reads x minus y is 0. That's going to tell me x equals y. And so my eigenvector is going to be the vector 1, 1. Why did I pick 1, 1 instead of a different vector? Well, doesn't friggin' matter. Like, it's only up to scalar multiplication anyhow. So you can pick any scalar for y, or sorry, any number for y, and that'll give you the number for x. So here I've got my eigenpair is 5 and 1, 1. In the lambda equals 2 case, right, I'm going to get 3 minus 2, 2, 1, and 4 minus 2. That's going to give me 1, 2, and 1, 2. Again, this is obviously singular. Great. I'm going to augment this by 0, so I'm going to do 1, 2, 1, 2 augmented by zeros. This is going to tell me x plus 2y equals 0. So I'm going to go ahead and pick some value for y. Don't pick 0, right? This is a pivot and free thing, right? So I'm going to pick my y as 1. So if y is 1, oops, that's not the symbol I'm looking for, then x has to be negative 2. And so my eigenpair is 2 comma negative 2, 1. And I'm going to bring my grapher back in here. And I'm going to say, all right, do those make sense in my context here? Oh, yeah. Sure enough, the red vector goes through 2, 2. So if I scaled this up to 1, 1, great. There's my output vector. That got multiplied by a factor of 5, right? It's up here at 5, 5. Cool. That one worked. This guy, if I put this back over here, that's negative 2 over 1 up. Exactly right. And that got doubled in length. Cool. That's exactly what I was expecting to see. This just went ahead and worked. I have another matrix here to look at. So here's my other matrix. So this matrix is negative 6, 3, 4, 5. And I'm just gonna use the grapher to look. So here's one eigenvector. And the problem is there's not another one. So that crossing was right there. There's this behavior, though. So this is an example of a matrix that has a positive eigenvalue. That's this red eigenvector goes with a positive eigenvalue. It also has a blue eigenvector, right? That's my input vector here. That got scaled to this output vector here. That scalar, though, was negative, right? So it got flipped around and stretched out. Both of those are options here. Okay. Last couple things on this. There are some matrices that don't have eigenvalues or that don't have real eigenvalues. So there's a little bit of... Okay, I lied. There are matrices that have eigenvalues that are complex, and there are matrices that don't have enough eigenvectors. So I'm just going to put that down here as a warning, right? Eigenvalues can be complex. They can also be repeated. So one where they're repeated would look something like the identity matrix has a double eigenvalue of 1. Sometimes you can find eigenvectors to go with that. Sometimes you can't. So there may not be an eigenvector or there may not be enough. It's kind of a weird way to say this. Eigenvectors. So what I mean by that is you may have a repeated eigenvalue that doesn't, so that eigenvalue might appear twice. It might not have 2 eigenvectors. In the case of the identity matrix, this thing has eigenpairs of 1 and 1, 0, and also 1 and 0, 1. So this is a matrix that has a repeated eigenvalue, but it has two eigenvectors. It's possible that you can have a repeated eigenvalue that'll have just a single eigenvector. That gets a little annoying for us, especially in DEs. So if you're in DEs, pay attention to this one. So this is especially an issue in solving differential equations. Okay. Last couple of things, just some kind of clean up some facts here. The product of the lambdas of the eigenvalues is the determinant of the matrix, and the sum of the lambdas is the trace of the matrix. I don't have much occasion to use these two facts, but they're just facts that you maybe ought to know. The book asks you a couple questions about these, so you just know that they're in there. And then there's a couple of more facts. If lambda and x is an eigenpair for a matrix A, then if A inverse exists, one over lambda and x is an eigenpair. Oops. I can write, I promise. Is an eigenpair for A inverse. That's relatively, like, we could see that relatively quickly, right? We're looking at AX is lambda x. If I invert A to the other side, right? If A inverse exists, then I could write x is equal to lambda A inverse x. I just sucked the lambda through A inverse because it's a matrix. And then I could just divide by lambda. So I'd get 1 over lambda x is equal to A inverse x. Notice that this would require that lambda isn't 0. So that's another fact I could add here, right? If lambda equals 0 is an eigenvalue, for A, then A is singular. And actually, this goes vice versa, right? So if A is singular, then lambda equals 0 is an eigenvalue. That's a convenient fact to know. And then one more little fact here. If lambda and x is an eigenpair for A, then lambda to the n and x is an eigenpair for A to the n. And that's what I need you guys to know for today. We're going to use eigenpairs a lot. So if this concept isn't clicking, hit me up. We need to get this concept to click for you. Thanks for watching tonight. Have a nice evening.